amount of excess charge on an ordinary object. The purpose of this lab was to determine an object's excess charge due to its interactions with other neutral and charged objects. The object of interest is a piece of tape that was initially neutral but became charged through contact with a neutral base tape. It was determined that the charge of a U-tape was 9.3 times 10 to the negative 9 coulombs. There was a deficiency of 5.8 times 10 to the 10 electrons on the tape, and the fraction of atoms that gave up electrons on the tape was about 1.5 times 10 to the negative 7. Some fundamental principles explored in this lab are that the interactions between charged objects is electrical force. Like charges repel and unlike charges attract according to Coulomb's law. The transfer of charges between neutral objects can occur through contact, and that net force is proportionally related to the change in momentum. In order to find the U-tape's charge, we need to see how it interacts with other objects that have known charges, such as a plastic pen. We know that a plastic pen becomes negatively charged when it's rubbed against cotton or hair. When placed near the plastic pen, the U-tape is strongly attracted, and based on Coulomb's law that unlike charges attract, we can assume that the U-tape is positively charged. Other initial data measured was the length, width, and mass of the tape used. The experiment to determine the magnitude of the U-tape's charge involved making two U-tapes and placing one of them between two books labeled tape B and approaching from the underside with tape A. Making the assumptions that air resistance is negligible, each U-tape has the same net charge and can be treated as point charges, we are able to identify that the net forces on tape B are equal to 0 at the point right before tape B begins to float due to the momentum principle. The gravitational force holding tape B down will be equal to the electric force exerted up on tape B due to tape A. The separation distance between the two tapes right when tape B began to float was 0.02 meters. The excess charge on the U-tape can be calculated by first calculating the gravitational force on tape B. Next, in order to calculate the electric force, we can assume that at the instantaneous moment right before tape B begins to float due to the electric force exerted by tape A overcoming the gravitational force of tape B, we can say that the net force is equal to the change in momentum in the y direction over change in time. The momentum would be 0 right before tape B begins to float, so electric force and gravitational force combined equal the net force on tape B, which equals to 0. We can now solve for electric force, and therefore solve for the charge, now knowing the electric force and distance d between the two tapes. The charge is equal to 9.3 times 10 to the negative 9 coulombs. We can estimate the fraction of total atoms that gave up electrons to form the positively charged U-tapes, first by calculating the total surface area atoms, using the tape's area and the area of an atom. Then we can calculate the number of deficient electrons or electrons lost due to the tape becoming positively charged. And using these two values, we can estimate that the fraction of total atoms that gave up electrons was around 1.5 times 10 to the negative 7 power. Here is the code and computational model representing the two U-tapes, where the red particle represents tape B and the blue particle represents tape A. The purple arrow pointing upward denotes the electrical force exerted by tape A on tape B, while the green arrow pointing downward denotes the gravitational force exerted on tape B. The two forces are equal in magnitude but opposite in direction at the point right before tape B is about to float due to tape A. And the charge of one of the U-tapes was determined to be 9.3 times 10 to the negative 9 coulombs, as was previously calculated. Here are some questions to think about regarding this lab. What if electrons had positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? The direction of the electric fields generated by the protons and electrons would reverse, meaning the electric field generated by a proton would now face toward the proton, and the electric field generated by an electron would face outward away from the electron. Also, the U-tape would now be considered negatively charged. However, the interactions observed during the experiment would remain unchanged, because Coulomb's law still holds true that like charges repel and opposite charges attract. Why is it important to handle the charged tapes as little as possible, and what happens when the charged tapes come into contact with your hands or other objects? The charged tapes coming into contact with your hands or other objects can lead to charge transfer between the objects, meaning that negative charges from your hand or other objects would transfer to the positive tape, attempting to make it neutral. The charged tape could ultimately lose all its excess positive charge and become neutrally charged, making it difficult to observe any interactions needed for the experiment. In conclusion, in this lab, we learned that the like charges repel and unlike charges attract according to Coulomb's law, and by balancing the Coulomb's law, the force of gravity, and Newton's momentum principle with the previous assumptions that the tapes can be treated as point charges floating above one another, excess charge could be calculated when the system's forces were at equilibrium. The excess positive charge on a piece of tape was estimated to be 9.3 times 10 to the negative 9 coulombs, which is in an acceptable range.